Oh, so now we're going to go over rational polynomials. The term rational polynomial harkens back to the term rational number, where a rational number was just the ratio of any two integers. Now, likewise, a rational polynomial will be the ratio of any two polynomials. So first, we're going to keep things simple and stick with the rational polynomials where the top polynomial is just a constant, and we'll do 1. So whenever we have 1 over x, the bottom polynomial is, of course, degree 1, and this is just the inverse function, which looks something like this, and then switches down to there. Okay. Now we have the inverse square function, 1 over x squared, where the bottom polynomial is of degree 2. And of course, these will be both on the top here. And if you do the cubic inverse, we're back to switching sides, but we do note that it'll shoot up faster and it'll slam in to the x-axis faster. And with the fourth root, right, it'll kind of the same thing, right? Comes down fast and shoots up fast. There we go. But the important thing to notice is that whenever the bottom function is an odd power, you switch sides. If the bottom function is even, you stay on the same side as you cross over the discontinuity that is present here at x equals 0. So whenever we have something more like this, we have a more general polynomial, we'll still be remembering this pattern that we saw here. So again, this is a type of equation called a rational polynomial. Note that the top polynomial is just a constant function in this particular example. Now, we have already seen that the lead term dominates a polynomial equation. And this holds true, even if the polynomial is in the bottom of the fraction, or which is also called the denominator of a fraction. Okay. All right, so for a rational polynomial, the lead term approaches the following. Let's go ahead and circle this right here. Lead term approaches the lead term of the top divided by the lead term of the bottom. So we want to keep this in our back of our mind so when we're working with these. So what is the, identify what the lead term is approaching. So using that convention, lead term approaches 1 divided by 2x to the 6. And then as x approaches infinity, this will simply be 0, right? We'd say as x approaches infinity. And so this means that our end behavior will be like this. All right, so on this one, we've got lead term approaches 1 over negative x to the 8th, which is going to 0, again, as x approaches infinity. And so our end behavior will be something like this, right? Notice how we've got what we're calling a horizontal asymptote right here and right here. All right, so here we got a lead term again that is approaching 1 over negative 5x to the ninth, which again is approaching 0 as x approaches infinity. Okay. And so in behavior will be like that. All right, so moving on to the next page. So we've got discontinuities of a rational polynomial equation. Discontinuities occur when you divide by, that's right, you guessed it, 0. All right, we can't divide by 0. So note that the graphs at the beginning of this lesson have discontinuities at x equals 0. So referring to these four equations, they all had discontinuities at 0. Now, it's worth noting that the polynomial in the bottom equation can also be written in a factored form that we see right here. So here is our expanded form, and then we have our polynomial in our factored form. And I'm using a D instead of C's for the other just to differentiate. There's no real big meaning behind using a D here instead of a C. So what happens as x approaches any one of these terms here, dn, d to the n minus 1, d2, d1, well, this will cause us to divide by 0, which gives us a discontinuity. So we're going to say this causes us to divide by 0, which causes a discontinuity. There we go. All right, discontinuity. All right, so go ahead and graph these three using a graphing utility. Take note of their behavior near their discontinuities. Let's take note of their discontinuities. All right, so we would say discontinuities would be, and I'm going to use the term x does not equal, -1 and +2. And here we can see that x does not equal, let's take note of the multiplicities as well, 2 and 1. X does not equal 1, 0, or 2. Noting their multiplicities of 3, 2, and 1. All right. So note right here, the discontinuity in the bottom for the first one would be I, an imaginary number. So this does not result in a discontinuity on the xy graph because x and y only include real numbers. So the x squared plus 1 does not generate a discontinuity, but we do have a discontinuity here at 0. And that occurs 4 times. Note that in this one right here, x equals 0 is not a discontinuity, right? Again, discontinuities only occur when x takes on a value that causes us to divide by 0. In this equation, when x equals 0, we are not dividing by 0. All right, so recall that you can find the lead term by multiplying the lead term by each individual term. And now we're going to determine the lead term and end behavior of the equations above. All right, so coming back to here, lead term of the bottom, B for bottom, is x squared times x. So the lead term of the bottom is x cubed. So we'd say the lead term approaches 2 divided by x cubed, which is 0 as x approaches infinity. Telling us that our end behavior is simply like this. All right, so right here, lead term of the bottom is simply x cubed, x squared, and then just x. X cubed times x squared times x, that is x to the 6. And so our overall lead term, which is the lead term of the top divided by lead term of the bottom, that's 10 divided by x to the 6, which is 0, as x approaches infinity. Again, giving us end behavior like that, right? We're slamming down into 0 in either direction for large values of positive or negative x. All right, so here, lead term of the bottom is simply 100 divided by x squared to the 5th multiplied by x to the 4th. And so that gives us 100 times x to the 10th times x to the 4th, or simply 100 divided by x to the 14th, which equals 0 as x approaches infinity. Okay, giving us end behavior with these horizontal asymptotes at y equals 0. Okay, so that's how we do that. Let's go ahead and do some curve fitting. We want to plot the vertical asymptotes on the graph. So we're not plotting, they're already plotted. We want to mathematically model the plot that we see. So let's go ahead and complete the following. So we're going to go ahead and put an A up there because that could be any number. We want to make sure it fits right. And so we've got discontinuity here, and that's at 2. And because it stays on the same side, we're going to say it's 2, multiplicity of 2. And here we've got at positive 1. Note how it changes side. So we're going to give it a multiplicity of 1. We're trying to stay with the lowest possible. And so discontinuities are either multiplicity 1 or 2 for right now. They can be higher, but we're just going to stick with 1 and 2. And this one's 3. Note how it changes side. So it is a multiplicity of 2. So we do right here, this would be x plus 2 because it's going to be negative, of course. So we'd write x minus negative 2, same as plus 2. Here, we got a square, so let's go ahead and fit. The square term is there, so let's go ahead and put the negative 2 right there instead. And we'll put since these change sides, at 1, we'll put the 1 here. And then for this last one, x minus 3, that goes there. Note how that one changes sides there as well. Okay, so let's clean this up. So we got a over x minus 1 times x plus 2, quantity squared, times x minus 3. So we're almost there. We still have to figure out this a term. We figure out the a term the same way we did for polynomials. That is, we find a point on the graph that's easy to work with. We got a y-intercept there at 0, 1. So let's work with that. So at 0, 1, we'll have 1 equals a over negative 1 times 2 squared times negative 3, giving us a over, so we would have negative times a negative, making that a positive. 2 squared is 4. 4 times 3 is 12. And so solving for a, we'll find that a equals 12. Plug this 12 into the original equation to get our mathematical model of 12 divided by x minus 1, x plus 2 squared times x minus 3. And that is our mathematical model for this plot, this data, right? Remember, this is kind of like representative of like what would happen if there were a bunch of data points, right? There we go. All right, next one, we're going to go ahead and just take this and we're going to graph this to, or sketch it to the best of our abilities. So first, let's note the discontinuities. Negative 3, which happens once. We've got negative 3/2, which again happens once. And then we've got positive 2, which happens twice, right? I'm just looking at the exponents. All right, so negative 3, negative 3/2, which is negative 1.5, and positive 2. And noting their multiplicities down here for reference. And now the end behavior, which would be 9 divided by x times 2x times x squared, or simply 9 divided by 2 times x to the 4th power. So we've got the end behavior that's going to be like that. And I know it's going to be above and beyond because the bottom here is a positive exponent. Okay. And so this point here, this is no longer a point we go through, remember. This is now a discontinuity. And we already know the x-intercepts for this guy because there aren't any. X-intercepts are going to be generated from the top of the rational polynomial. So just kind of coming off this, graph that part right there, right? Because we can't cross that discontinuity. And this is an odd, so we change sides. Okay, again, don't really know how far we come up. You can just throw in a few test points if you want to increase the fidelity of the graph, but that is not necessary. Let's go ahead and find the y-intercept, though. Y-intercept happens whenever x is 0, so just plug 0 into the equation, and so we've got 9 divided by 3 times 3 times negative 2 squared, so essentially it'll just become 1/4. So we've got our point right there. And because that's 2, we stay in the same side. And there we have it. There is our sketch of the graph. I encourage you to plot this into a graphing device to see what it looks like.